Hello, welcome to a continuation of our study on the carbonyl carbon chemistry. Let us look at the nitrogen nucleophiles. And here we are going to consider primary amines which will transform a carbonyl into what is called an imine, this functional group. Or we can use secondary amines which will transform the carbonyl into what is called an enamine, that functional group. Those R groups are alkyl groups attached to the secondary amine. Okay, so what is the mechanism for these processes? Let us start with the imine. This reaction takes place at a pH of between 4 to 5, okay, so that the amine could still be nucleophilic enough. So we are going to use the primary amine to do nucleophilic attack on the electrophilic carbonyl carbon to break up that pi bond, so we end up with an alkoxide. The alkoxide then picks a proton to form an alcohol. Now remember, this nitrogen now has 4 bonds, so it undergoes proton transfer to form what is called the carbonylamine. So look at where we started. We started on the carbonyl and we want to head over here. We've made a few steps, so we just need to kick out this hydroxy group. So that means we need to transform it into a good leaving group. So we can do a proton transfer, which transforms it into water. Then we initiate the loss of the leaving group using the lone pairs on the nitrogen of the amine. Then after that, we can do a proton transfer to get us the final product. How about if we want to form an enamine? If you want to do that, the first step is going to be the same. The second, third, fourth, and fifth. The difference is in the final step because for secondary amine, this proton is not going to be there. So instead, we are going to have something like this. Nitrogen, and assuming the R groups were ethyl groups, so we're going to have the ethyl groups attached. And if you're using secondary amine, then what happens is we're going to remove a proton from the adjacent carbon because there's no proton on the nitrogen. Okay, so we're going to remove a proton from there using the secondary amine. We use those lone pairs to remove that proton, and that goes there, and that goes there, and then we end up with the enamine. Okay. The strategy of imine formation can be used to transform a carbonyl into an alkane through a process that is called Wolff-Kishner reduction. How do we achieve this process? Well, we can use hydrazine, which undergoes the same mechanism similar to the imine formation, and it yields what is called hydrazone. The hydrazone is directly reduced to an alkane if we use a strong base. Let us see how that works. So we can start from here, because already we know how this is generated through the imine formation. So in the presence of a strong base, we can do a proton transfer, and those electrons go to the nitrogen, so we end up with nitrogen connected to hydrogen. 1, 2, 3, 4. Okay, and then we can have those electrons move there, and those ones go to the carbon, which is kind of just a resonance structure. So there's going to be 1, 2, 1, 2, and then a minus charge, nitrogen. Okay, and we generated water. So in the presence of water, this is going to pick a proton, and that goes there. So we form nitrogen connected to that and that. Now we have a hydrogen installed there. In the next step, we can use the hydroxyl group again to do a proton transfer. That goes there, and that's going to form a nitrogen, because we have a nitrogen-nitrogen triple bond, which is a nitrogen gas. So this reaction is kind of explosive because of the release of the nitrogen gas. So we form this stuff over here, minus charge 1 2 connected to that, and of course plus nitrogen gas. And then it's going to pick a proton from water, that goes there, and we form the product, and of course we regenerate the hydroxyl group. Okay. Next, let us look at the carbon nucleophiles, and this includes Grignard reagents, which we already discussed before. We could also use a cyanide, for example, potassium cyanide as a source of cyanide to attack the electrophilic carbonyl carbon, and then that breaks that pi bond, and we can follow that with a proton transfer. The source of proton could be hydrogen cyanide, or in some cases hydrochloric acid, which forms the cyanohydrin. The nitrile in the cyanohydrin can be reduced to an amine if we use lithium aluminum hydride followed by water as a source of proton. Or we can oxidize it to carboxylic acid if we do that under acidic conditions. But this reaction is often too slow to be practical. Another carbon nucleophile, which we have never learned about before, is the one employed in the Wittich reaction. So this involves the use of triphenylphosphine in the presence of an alkyl halide. Like in this case, we have methyl iodide. So this is going to do an SN2 to form carbon, and that carbon now, well, it has three hydrogen atoms, and then we follow this with a base. So we do a proton transfer. So butyl lithium 2 3 4 1 2 minus charge stabilized by lithium, and this is going to pick that proton that goes there, and we end up with PH3 PCH2. This is actually same as, or it can be written as PH3 CH2. Okay, so this is the same thing. We call this the eyelid, and this is the carbon ion that you see here, the carbon nucleophile that we are going to use. So in the presence of a carbonyl, we can use the CH2 1 2, the minus charge connected to PH3 with the plus charge, and this is going to attack that, and that goes there. So we end up with 1, 2, and we have oxygen attached to triphenylphosphine, which is then attached to CH2, and that is attached to phosphorus. Okay. Now, the phosphorus has higher affinity for oxygen. So what happens is just a rearrangement. This one goes there, this one comes here. So we form 1, 2, 3, 4, 5, 6, and it's going to be a CH2. So we have formed an alkene plus triphenylphosphine oxide. Okay. The carbonyls of aldehydes and ketones can also be oxidized using peroxy acids like MCPBA or peroxyacetic acid to transform them into an ester. A cyclic ester is called a lactone. So what you see here is that it just inserts an oxygen atom in between. So this was 5-membered, now we have 6-membered with oxygen inserted in between. If we have acetone, then what it's going to do is just to insert oxygen over there. Okay. How about if these two groups are not similar? Okay. If they are not similar, then what happens? We are going to follow this order. The group that's migrating is going to follow the order of hydride. It's easy for hydride to shift than the tertiary alkyl group, than the secondary alkyl group, primary alkyl group, and then the methyl group. So here we have these two groups that are different. Of course, this is a methyl group, and this is a secondary. This is attached to 2 carbon atoms, so we're going to say that this is a secondary alkyl group. So the secondary alkyl group is going to be the one that's going to migrate. So the product will look like this. That attached to oxygen, and then we have that group. Okay. What is the mechanism of this process? Well, let's look at what takes place. So we have that one. Let us use the simplest, like acetone plus peroxyacetic acid. So that is, it's going to be attached to oxygen, which is going to be attached to that. So we're going to use these lone pairs to attack that, and that breaks the pi bond, and we end up with 1, 2, minus 1, 2, 3, 4, 5, 6. And this is now attached to an oxygen. It's attached to another oxygen, which is attached to that, and that has a formal charge of 1. Then we can do a proton transfer. Remember where we're heading to? We have started from here. What we want to form is that one. We want to slide or to kind of shift one of the methyl groups to be attached to the oxygen. So in the first case, what we are doing here is simply a proton transfer. So we can form this compound 1, 2, 1, 2, 3, 4, 5, 6 minus. Then we have that attached to that. It's now attached to a proton, so it has a formal charge of 1. So what we want to do is to bring this one here, and then this is going to shift and get attached there, and this is going to go here, and then this is going to go here. Okay, so we end up with 1, 2 bonded to an oxygen. The oxygen is here, and now we have a methyl group attached to the oxygen plus carbon. Well, we have a double bond here, and then we have that, and then we have an OH. So we have generated a carboxylic acid and an ester, and this is what we were interested in. Alright, thank you for watching and have a good one.